Hey guys, so I wanted to take a couple of minutes and go over some of the key things in the test review. So this is part one of gas laws, and we're going to talk a little bit about gas behavior, kinetic molecular theory. We're going to talk about the relationships between the variables that we've been studying, and then what these graphs should look like. And then in part two and three, we're going to go over some of the math and work through some of the sticking points that students have been having. All right, so let's dive into it. So basically, we started out this unit talking about kinetic molecular theory. So you can imagine gas particles like tiny invisible ping pong balls, and they're constantly bouncing around in a room or a container, and they move in straight line paths until they hit something like maybe a wall or a balloon. So here, this is straight line paths. All collisions between gas particles are perfectly elastic. So basically what that means is that when they hit something, they bounce back without losing any kinetic energy. Kinetic energy. And then it moves on to say that the pressure is a result of the collision between gas particles and their container. Gas particles and their container. So yeah, you can imagine the tiny gas particles are like hitting the wall of that container. And most of the volume of the gas is empty space. Okay? It's because the particles are so small and spread apart. All right. So if you have a room full of kids, for example, running around and bumping into each other, they would never get tired. They just keep bouncing off the walls of each other and off the walls and each other. Okay, so let's talk a little bit about some of the conditions that we need to have an ideal gas. All right, so we've been talking about an ideal gas this whole time. All right, and so we've talked about some of those conditions here. We have elastic collisions that lose no energy. Another thing is that we know that in an ideal gas, the particles are not attracted to each other. Okay, that's one of the assumptions that we have. So it says gases are attracted to one another in a container. Is that true or false? Well, because one of the conditions of an ideal gas is that they aren't attracted to each other, we know that that has to be false. Okay, because the gas particles are not attracted. Not attracted in an ideal gas. All right, so they're not attracted. All right, in your own words, it says to define gas pressure, volume, and temperature. All right, so let's think about this. Gas pressure, we said earlier, is how hard and how often gas particles are hitting the wall of a container. All right, so that really is what it's about. It's about the collisions. Okay, it's about collisions of gas particles with their container. Collisions with their container really being like the key words to think about. So the more gas particles or the faster they're moving, maybe because they were heated up, you increase pressure. So that is the story with that. Okay, so volume. And volume is a common term that we've used and you've heard before, of course. It's just the amount of space the gas is taking up. So amount of space the gas is taking up. And for temperature, temperature has to do with how fast these gas particles are moving. All right, so the higher your temperature, you're going to have a faster moving gas particle. You'll have more collisions. You'll have more pressure. All right, so we want to think about the speed of the gas particles increasing. Really what it has to do with is energy being transferred from one source to kinetic energy. Okay, and so then you have that kinetic energy has raised in your system there. And so now you have got faster moving particles in there. So speed of the gas particles, that's what I really want you to remember about this. It's increasing, basically as your temperature is increasing. All right. So it says gas variable relationships. So before we dive into the gas variable relationships, let's just talk a little bit about some of these gas variable units. All right. So we had units for pressure. So pressure, really, we've studied mostly three. There are more, but mostly we have been working with atmospheres. We have been working with millimeters of mercury, and we have been working with kPa. All right. So that's generally what those are in. And volume, most of what we've seen are in liters. You could see other units of volume, but I want you to focus on knowing that when you see liters, we're talking about volume. And temperature is degrees Celsius, but in gas laws, we have to convert them to Kelvin. Okay, so it's degrees Celsius plus 273 is Kelvin, which is our actual unit for temperature in these gas laws. All right. Okay, so gas variable relationships. So here we're talking about some of the different laws that we have studied. All right, we know that pressure and volume are inversely related, okay, because it's P1 V1 equals P2 V2. All right, that's an inverse relationship. So it says as pressure increases, the volume has to decrease, because in an inverse relationship, when one goes up, the other goes up, or down. So basically in the opposite direction. So it says pressure increases, therefore our volume decreases. And so, yeah, that's Boyle's law. And then it says as temperature increases, what happens to the volume? Well, if we look on our reference sheet, we see that temperature are related to each other by Charles's law. And it's a direct relationship. In fact, all of them are that we're studying here, except for Boyle's. So to make it easy, you can remember, oh yeah, pressure and volume, Boyle's, that's the one that's inverse. So Charles' law says as temperature increases, volume must do what? Well, if it's a direct relationship, it must increase. And then over here, now we're talking about moles decreasing in volume. So moles and volume was Avogadro's law. And again, that is going to be a direct relationship. So as moles decrease, volume must also decrease. And then as temp decreases, our pressure will do what? Okay, so temperature and pressure. So of the ones that we learned, it's the Gay-Lussac's law. So Gay-Lussac's law is the one where temperature and pressure were involved. Gay-Lussac's law. All right, so as temperature decreases, pressure decreases. We know that it's a direct relationship because the only one we've studied is Boyle's, that's inverse. So when you have an inverse relationship, your formula looks kind of like this. But when you have a direct relationship, we have more of this division set up. So for Charles, it is V1 over T1 equals V2 over T2. And you will have these formulas to reference, all right? And then for Avogadro's, we had V1 equals N1, V1 over N1 equals V2 over N2. All right, so there's that. And then finally, we have Gay-Lussac's law, which is a direct relationship between pressure and temperature. So P1 over T1 equals P2 over T2. And so I'm not going to get into the math aspect of this yet, but remember, it's our direct relationships. These are the ones where we cross multiply and divide. Okay, so I just wanted to show you here what these look like next to each other, so you can make the connection that when you are talking about these multiplication formulas, then you are talking about an inverse relationship. And when you see things that are written more like this, you know that we're looking at a direct relationship. And I'm going to skip number 4 and come back to it because this kind of makes sense in terms of the flow of this. So when you sketch an inverse relationship, all right, so if you were to, plot out actual data of pressure and volume that maybe you collected, and we did this in our simulator on the computer at the beginning of this unit, your graph is going to look something like this. All right, it's curved. All right, so you have a curved graph when you have an inverse relationship. And when you have a direct relationship, you're going to have a straight line. Okay. All right, so let's go back up to number 4 before we conclude this part. It says list ways to increase pressure of a gas in a container. So let's look at these equations, okay? So if you don't want to memorize what ways you can increase pressure of a gas in a container, you can go look at the relationships that we have written down over here. So I see pressure over here in a couple places. So I've got pressure here, and I've got pressure here. And so in an inverse relationship, we know that when one goes up, the other must go down. All right, so inverse is when one is going up, the other must go down. So it says we want to know about pressure increasing. Okay, so pressure will increase when volume decreases. So decreasing the volume is one way that you could increase pressure. All right, let's look at this other one down here. We have a direct relationship now. So we know that this one relates to pressure and temperature. So in a direct relationship, when one goes up, the other goes up, or when one goes down, the other goes down. So in this particular case, if we want pressure to go up, this other must also go up, which is temperature. Okay, so raising the temperature or decreasing the volume, those are two ways that you could increase the pressure in your gas container system. All right, hopefully that was helpful. I've got a couple more videos coming going over some of these math problems, and hopefully if you are stuck, we can get you through it. Thanks.